Our next topic is on chemical equilibrium. So under this topic, we're going to cover equilibria for gaseous and heterogeneous reactions. So we'll consider types of equilibria, but before that, we are going to define what chemical equilibrium is. And then after that, we will define what equilibrium constant is, different types of equilibria. Then we will apply the equilibrium constant concept and look at the factors that affect equilibrium, chemical equilibrium for that matter. So we look at the effects of changing the reaction conditions on chemical equilibrium. So equilibrium is a state in which there are no observable changes as time goes by. So when you look at a particular system, whether it is a flask containing an amount of water and you cannot observe any change, then you can say that it is in a state of equilibrium. This can also be observed in chemical reactions. And the chemical reactions that where you can observe equilibrium is where you have a reversible reaction. So when a chemical reaction has reached equilibrium state, the concentration of reactants and products remain constant over time, and there are no visible changes in the system. So a simple example is when you have a reaction where you have, say, A plus B, okay? And these reactants react to give us, say, C plus D, okay? For a reaction that is one directional, the reactants react and give the products, okay? But for reactions that are reversible, we have the reverse reaction taking place here. So we have A plus B reacting to give C plus D, and then C plus D reacting to give A plus B. So it's giving A and B, okay? So when you have such a reversible reaction, both forward and reverse reactions are taking place. At the beginning, of course, you only have the forward reaction, and then the reverse reaction starts taking place. So it reaches a point where it's as if you cannot observe any change. And we will see at a couple of examples which will illustrate this state of equilibrium. So it's as if there's no reaction taking place on you, if you can observe it. But in real sense, the forward and reverse reactions are taking place. So when a chemical reaction has reached an equilibrium state, the concentration of the species in this reaction, that is the reactants and the products, are constant. Okay, so that means when you have attained equilibrium, then you have what we call equilibrium concentrations of the species. Okay? It's like there's no change happening. It's as if the concentrations are constant. But in real sense, there is a lot of activity happening in the molecular level. So you have A and B reacting to give C and D. And then you have C and D reacting to give us A and B. Most chemical reactions are reversible to some extent. So then we can say that a certain type of equilibrium is established for these chemical reactions. So like the example that we looked at, or A plus B giving us C plus D, at the start of a reversible process, the reaction proceeds toward the formation of products. So at the beginning, you only have A and B reacting to give us C and D. But then as soon as some product molecules are formed, the reverse process begins to take place. And the reactant molecules are formed from the product molecules. Chemical equilibrium is achieved when the rates of the forward and reverse reactions are equal and the concentrations of the reactants and products remain constant. So this example that we looked at, there is the forward reaction occurs at a certain rate and the reverse reaction occurs at another rate. Okay. Now, when those two rates are equal, then you have chemical equilibrium having been established, and the concentration of the reactants and products are constant. So, as we said, then you have equilibrium concentration having been reached. Apart from chemical equilibrium, we also have some physical equilibrium. This is an example of physical equilibrium. So for example, the vaporization of water in a closed container. So when you have, say you have water, liquid water in a beaker like this, and then it's covered, it's enclosed. So that means although the water can escape from the beaker, it does not completely escape from this enclosure here. So at a given temperature, even at room temperature, there is a tendency of water vaporizing. So you have the vaporization taking place. Okay. But at the same time, as soon as the vapors are formed, there is also a tendency of the vapors condensing back here into the beaker. So there is a vaporization process and a condensation process taking place. Now, once the rate of vaporization is equal to the rate of condensation, then you have an equilibrium having been established at that given temperature. So this is a simple example of a physical equilibrium, and we call it physical because water essentially is not changing in its nature, chemical nature, but what is happening is that it is changing from liquid to gaseous state and then back. Just the physical state that is changing, but not the chemical state of water. So let's look at this example here of example of this reaction where you have N2O4. It can exist at equilibrium with NO2. Now, the beauty of this type of this example of a chemical equilibrium is that you can observe it by changes in color. So at first, if you start with only N2O4, it is a colorless gas. And it has a tendency to dissociate to give us brown NO2 gas. Okay. So you can, if it is in a flask, then you can observe this change by the browning of the contents of that particular flask. Okay. And then the reverse reaction also is taking place at the same time. So we have the dissociation of N2O4 taking place to give us NO2. and then NO2 combining to give us N2O4. So the forward and reverse reaction are taking place. And this continues until you reach a certain point where equilibrium has been established. So the rate of the forward and the reverse reactions are equal. And then you reach equilibrium concentrations. So that means the concentration of these species, that is N2O4 and NO2, are now constant. So this happens when equilibrium has been established. We can look at different examples here where we have different starting concentrations. So for example, this first example here, we are starting with NO2 at a particular concentration up here. And then N2O4 is not there, it's zero. The concentration is zero. But as time moves on, NO2 starts combining to form N2O4. So you have N2O4 starting to form here. Okay? And the concentration of NO2 decreases along that line as the concentration of N2O4 increases. So the NO2 decreases and N2O4 increases. These trends are followed until the equilibrium is established. So at that point, we have equilibrium concentrations having been established. So we see that the concentrations of the two species are constant at a certain point in time. Okay. We can consider this second example where now you are beginning with N2O4 at a certain concentration and you don't have any NO2. So as time goes on, the concentration of N2O4 decreases because it now forms NO2. So you have the concentration of NO2 increasing and that of N2O4 decreasing, and until a particular point in time where equilibrium has been established. So we have the concentrations of the two species being constant. So these now are the equilibrium concentrations of the two species. Okay. We can also have another example where you have the two species at the beginning. So you have the two of them at a particular concentration. This is the concentration of N2O4 and the concentration of NO2. So both of them are in the flask. Okay. So the concentrations change. Here you see that of N2O4 increasing slightly and that of NO2 decreasing with time. Okay. Until you reach the equilibrium state where now the concentration of the two species are constant. So we have equilibrium concentration having been reached. Okay. Now, if you look at these three examples, notice that equilibrium concentrations are not the same. They vary depending on how much of the species you begin with at the start of the reaction. Okay. So if you consider cases where you have different concentrations of the species at the beginning, starting, these are initial concentrations. Notice that at equilibrium, you're going to have also different concentrations of the species. Okay. So different starting concentrations or initial concentrations, we have different equilibrium concentrations. Now, if you are to find the ratio of NO2 to that of N2O4, which is this, you notice that you get, you can try this out in your own time as well to confirm these figures. Notice that you get different values, okay, of that ratio. But if you find the ratio of NO2 squared over N2O4, okay, you get a value that is almost constant. Okay, it's not constant. There's a slight change, very minimal change, but essentially it's as if whatever you are getting is a constant. So this particular value that we get here is essentially what we call the equilibrium constant, because this ratio is determined from the equilibrium concentrations. You square the concentration of NO2 divided by the equilibrium concentration of N2O4. You get a constant that we refer to as the equilibrium constant. So notice here the NO2 concentration is squared. And when you look at the reaction that we had, that was N2O4 gas, okay, it dissociates to give us NO2, okay, and here we had 2. So notice that this square here, or this power to power 2, is the same as the value of this coefficient here. Okay, so that means we can come up with a general expression for the equilibrium constant. So if you look at this reaction, this is what we got. We got K is the equilibrium constant. It's given by the ratio of the square of the concentration of NO2 divided by the concentration of N2O4. The average value of those values of K that we got is 4.63 times 10 to power minus 3. So if you consider a general expression like this, where you have A plus B reacting to give us C plus D, and then there's an equilibrium existing, when you consider the coefficients as well, so K would be given by concentration of C to power C, that is the coefficient, times the concentration of D to power D, divided by concentration of A to power A, and concentration of times the concentration of B to power B, which is the coefficient. Okay, so this is a general expression for the equilibrium constant of a particular reaction. Okay, like in this case, we have this general expression. Now, this expression is called, it's a mathematical expression for what we call the law of mass action. Okay, and the law of mass action simply states that for a reversible reaction at equilibrium and a constant temperature, a certain ratio of reactant and product concentrations has a constant value, K, that is the equilibrium constant. Now, this equilibrium constant is the magnitude or the value of the equilibrium constant is very important, because it tells us whether an equilibrium reaction favors the products or the reactants. Okay, if you look at this example of this reversible reaction, the magnitude of this K depends on which side is favored. So for example, if the product side is favored, meaning that more of products, you have a higher concentration of products than the reactants. So in that case, this ratio here, or this product here, is going to be at a higher value than the denominator. Okay. If, on the other hand, the reactants are the ones that are favored in this reversible reaction, then you're going to have a high value of this denominator compared to the to the numerator. Okay, and this one we can measure in terms of the magnitude for us to know which side is favored. So for example, when K is so much greater than 1, it means that the product side is favored. So you have more of products being formed. And for K to be so much greater than 1 here, if the value is greater than 10. When the value is greater than 10, then we say that K is so much greater than 1. If on the other hand, K is so much less than 1, it means that the reactants side are favored. Okay. And for a value to be considered to be much less than 1 is when it is less than 0.1. So if it is less than 0.1, then we say that K is so much less than 1. And in that case, the product's side is favored. No, the reactant side is favored in this case. So maybe you may wonder why is it important to know the equilibrium, chemical equilibrium, and also to determine the equilibrium constant of a particular reaction. For an industrial chemist who wants to maximize the yield of a particular product, so here I give an example of sulfuric acid, the industrial chemist must have a clear understanding of the equilibrium constants for all the steps in the process, because you know the production of sulfuric acid, there are several steps, or there are several reactions which are reversible, and these reactions have equilibrium constants. So it's very important for the industrial chemist to have an understanding of the equilibrium constant for all these steps, starting from the oxidation of sulfur all the way to the formation of sulfuric acid. So this is just a simple diagram showing the different steps. So the first step is the oxidation of sulfur to give us SO2, sulfur dioxide. And then the second step is the oxidation of SO2, okay, to give us SO3. And then the third step is where now sulfuric acid is formed. Eventually, you have the vapors of sulfuric acid, which is then now mixed with water to give us the final concentrated sulfuric acid. So an industrial chemist will need to know the different, the equilibrium constants of these different steps, so that he may maximize the production of sulfuric acid. Because it is a reversible reaction, you know that the conditions have to be set in such a way that it favors the forward reaction in each step. Okay. In terms of the units, the units of the equilibrium constant. So since you saw that it's a ratio of the product concentrations divided by the reactant concentrations. So usually the units are not included. And the reason why they are not included is that the concentrations that are in the expression for equilibrium constant are not considered as concentrations, but are considered as activities. Okay. And by activity, you just divide the concentration. For example, if it is in molarity, you divide it by a standard value that is 1 molar. So for example, if you had the concentration of your species maybe is okay, maybe the concentration of just a second. If you're talking about the concentration of a particular species A is given by maybe 0.1 molar. Okay. So what you use in the equilibrium constant expression, or to determine equilibrium constant, is going to be 0.1 molar divided by 1 molar. So the units cancel out. So essentially what you're going to work with is the activity of that species. That is 0.1. And then, as you will see, the equilibrium constant can also be determined by the partial pressures of the species, especially when you're talking about where you have gaseous species in the reaction. So then if you're talking about partial pressures of these species, then you would divide those partial pressures by 1 atmosphere. So you convert them to atmospheres and then divide by 1 atmosphere. So the units cancel out. So this explains why there are no units for the equilibrium constant.